Hello, welcome everyone. We're about to start our first lightning talk session of the day. We've got a wonderful collection of talks for you. These folks have been using federated and related technologies, primarily Flower, to build some pretty cool applications. So feel free to keep on building. If you want to take a break and listen to these talks, that's also really cool. But with that, I'm going to hand over to our first speaker. Here's Adaway Kanhadi. He's from Johns Hopkins University. He's been using Flower, I think, for a number of years now, been a passionate user, built amazing federations with us. And I'm delighted to hand over to him to tell us all about his past, present, and future work. So over to Adaway.
Thank you, Nick, for the great introduction. Hi, everyone. Very nice to meet you all. Please continue hacking. Don't mind me. I'm just going to continue talking. Thank you. I'm Adway Kanhere. I'm a CS PhD student from Johns Hopkins, and I'm here to talk about heterogeneous medical image segmentation with NN, UNet, and Flower. So this project was the culmination of part of my application to the Flower Next pilot program. And for you hackers who are seriously thinking about, you're super interested in FL down the line, which I think you will be after this hackathon, please check that out and please do apply. I think it's a wonderful program, and you get a lot of support from the core team of Flower. So I'm going to talk a little bit about, my talk is mostly going to be about medical image segmentation because that's sort of my domain of expertise. So within medical image segmentation, we have image segmentation as the most common downstream application, and that's usually used as sort of a first step for further downstream clinical outcomes correlations. But sourcing training data for medical imaging is hard. And there are three reasons why. We call this the 3V problem. It's the volume, variety, and veracity. You usually have large amounts of data, but that needs to be manually annotated, and creating those annotations is expensive because you have to get doctors to sit down and then manually annotate your data for you, which is expensive, and usually doctors are very busy. And variety is that you have imaging data, which is usually non-IID, so you have different modalities, you have different scan types, and so things can get heterogeneous very fast, and this is usually a common bottleneck for developing FL applications. And veracity is images of different views. So for example, you might have a full body scan, or someone might just take a scan of your brain, or someone might just take a scan of your chest for an X-ray. And so again, you have images with different views. And so that adds a layer of complexity on top. On top of that, you have algorithmic development or sort of challenges as well. And it's usually that when you're training certain models for particular organs or regions of interest, you end up training models which have a very narrow focus. So they're only segmenting that one particular organ. And what you end up with is several models that are usually trained on the same data, and this also decreases clinical translatability. And the last problem that I want to also talk about was that specifically in the field of medical imaging, you also have the problem of incomplete annotations. And so what this means is you have different sites with different images containing the same organs in the same field of view, but in your training data, if you do end up using it, you'll only have one organ that's annotated. And so we call this like partial labels or partial annotations in computer vision. And so the problem here is, how do we build a solution that can collectively aggregate knowledge from all of these different tasks, from these different modalities, into a single unified model? And if we have a single unified model, this is great because you can just share this model to your collaborators, and probably they will just fine tune or just run inference on the n number of tasks that you have. And so federated learning is the perfect solution because in this case, you're not sharing the models you're sharing the models instead of sharing the data, right? So it's also privacy preserving. You don't have to worry about asking the other institutions. And in the case of medical imaging, it's usually very hard to source data from a different institution for HIPAA and other privacy constraints. And so there are a bunch of methods in this domain that talk about how you can build FL for non-IID data, but they weren't really successful for medical imaging. And so we wrote a paper about this, which was published at CVPR 2024 at one of the workshops, and this was privacy preserving FL. And the main idea was we were selectively aggregating parts of the network that we felt were most important for knowledge aggregation, and then using that to train an FL setup to effectively have a federation which can learn from different clients and completely different tasks. And so the next part of that, and what I'll be mostly focusing on today, is we realized that we want to focus on one particular library, which is NNUNet, which is very popular, almost a baseline state-of-the-art library that any medical image analysis group will use as a baseline for training medical image segmentation models. But the problem with NNUNet is that it's very popular, but it's complicated because you have to set it up. Usually needs a server with a large amounts of compute, and you usually need to set up these training scripts to effectively run your medical image segmentation pipeline, and it does not natively support federated learning out of the box. And so we did have one project, which I would like to mention, which came up when we were developing this, which was Project Kapana, which helped basically federate NNUNet for you. But again, the problem there was it required you to deploy this on like a giant GPU cluster, and it wasn't really usable for a lot of groups. And so we realized that this is a gap in the current state of the art. And so we wanted to see if we can use Flower and its lightweight APIs to see if we can sort of deconstruct NNUNet and then use Flower to basically federate the medical image segmentation problem while also sort of keeping it heterogeneous, multitask, and all of the good stuff. And so this was our setup. We developed the code, and I'll go into that in a bit, but effectively what you have is you have the Flower superlink, so you guys will probably be hacking at it today, but you have the Flower superlink, which is the server, and you have clients, or basically research labs or institutions as your supernodes, and every supernode they can have common data, they can have common modalities, or they can be completely heterogeneous. But the idea is that you want to have this federation where you have supernodes and multiple different clients connecting together and collectively training a unified segmentation model, which you can then use for downstream tasks. And if a new server or a new client node that comes in, so for example, if you have a new research institution that comes in and wants to use that particular task and they don't have data, they can still just download this server model from the server and then just run inference without having to source the data again, without having to train any more new ML models. And so, yeah, again, please don't mind me, but this is the link to the GitHub. If you're interested, you can check it out. And we did do this, and we were able to successfully integrate Flower natively. So this uses completely Flower to set up the clients, to set up the server. It supports heterogeneous modality, agnostic medical imaging. So you can have clients with completely different tasks. You can have clients with completely different data sets, and it still works. It can be extended to be model agnostic. We've chosen NNUNet, as I mentioned, because this was like a need that we thought we wanted to focus on. But again, you can use the code, change the model, and you can have transformers if you want, or any other different model that you'd like. And again, the script automatically adapts the best parameters because it selectively aggregates only those layers, except the first layer and the last layer, which is usually what we've noticed, which leads to personalized sort of FL. It just doesn't aggregate those layers, but it sends the rest of the weights in sort of, we have like a smart logic that selects what parameters get sent to the server. And on top of this, again, because this is built natively in Flower, you have all the advantages of Flower that you can use. So you can have a DP filter on top, you can have any other privacy filters that you'd like, and you can add on to it, and it's as simple as like one line of code, and you can see that in the Flower docs as well. So we were also really fortunate to have a real-world demo. I'll talk a little bit about that. So what we got a few medical institutions from the US and from the UK, and we had Flower, who so graciously were kind enough to help us set up the federation. So they set up the server and they allowed us to orchestrate this process. And so we're in the process of running this, and we'll share updates when we have the results. So we're in the process of setting up this federation and effectively testing out on different data sets and different clients. So to wrap it up, again, thank you to all the friendly folks who've made this possible. So thank you, Nick and Javier, for giving us the opportunity to be a part of the Flower Next program, for Javier for helping us with the technical, all the setups. And then also thank you to all our collaborators who helped be a part of this federation to sort of test out the demo. So it was Dr. Peter Kamal from MD Anderson, Vish Kumar from Stanford, Eden Rafel from UCL, and Fan Zhang from the University of Cambridge. And that is all I have for you today. Please feel free to go back to hacking. If you have any questions, I'll take questions.
Maybe I could take the microphone down. Thank you, Edaway. That was amazing, amazing stuff. We're just going to set up now for the next talk. Let me just quickly do a switch to the slides. Go to present mode. Okay, we're ready. Okay, so it's my pleasure to introduce our next speaker. I met him just this morning, but I'm incredibly impressed by what he's built and where he's headed. He's been looking into an incredibly important problem in a similar domain, but in the world of dentistry. He wants to make it federated, use more data, simplify the process. His name is Eric Chong. I think you guys should all listen to what he has to say, and you can see how you might want to build something or collaborate in a similar fashion. So over to Eric.
Thank you, Nick. Appreciate it. Thank you, Nick, and the Flower team, and everybody that is here. So good to see you all here. You know, a lot of people don't really think about healthcare until you get sick and you have to interface with the healthcare system, and then it becomes a very real issue. So I'm going to start with a quick quote, and I love when Hippocrates says, "The greatest medicine is teaching people how not to need it." And so this isn't exactly on point, but this is one of my side projects that I'm working on. And if it wasn't for Flower, I don't think that this would be possible. It's actually a concept that I was thinking of for a long time. So $50 billion are wasted every single year, and there's denials. As a patient or as an individual that's getting care, it might just look like you are being denied. You're being told no. I like to use the word gaslit into being told that you're wrong, but it's just zero prediction. So what we did is we wanted to create some visibility and actually allow doctors, dentists, patients to collaborate their information so that they can fight the insurance companies back for the money that they should have for their care. So that's what it's all about. I'm building an architecture with Flower that allows all of the private health information to stay inside the local dental practice. Because if you know, and if you've ever been to one of these dental practices, a lot of them are still using local servers, and they're completely air-gapped, and they're just running inside their offices. So it allows the patient information to stay there. Then we have these local nodes that's going to allow the predictions to happen. And then, of course, with Flower, we can send those updates to update the model, and we can have this federated learning happening. This is all really rapid build. I've just started this about 48 hours ago. So I have some snippets of code, and this is something that I am currently in the process of putting up, so I'll be available for repo. I was trying to get it to upload to my website. So none of this website's working, but it will by the end of today. And you can try the demo yourself. What I built is a way for dental practices to collaborate all of their claim information that they send to insurance companies. This is what I did, by the way. I was in the medical field, or in the dental field, and I did medical billing for them. By the way, if you haven't heard of that before, it's because 98% of dental practices don't do this. And they tell people that you cannot use your medical insurance at a dental office, and it's a lie. It's because they do not have a medical billing department. So the same problem with dental insurance. If we could just take all this claim information and allow other dental practices to learn off of it, we're going to see a lot less denials. And really what that means is it's not about the insurance companies paying out or not. It's about patients getting the care that they need. So that's it. We're going to create, here's a little bit of file tree. Let me see. The model is just to get as many dentists on board. And the great thing about this is that it's a network effect. The more dentists on board, the better this is going to work. I know that they were just sharing this medical imaging was able to improve about 33%. I don't know where we're going to land, but I know that we're going to save a whole bunch of money for the patients and the providers. So that's the goal. Yeah, you can find me. My name is Eric Chong. I literally have that domain there, and that's it. It's blank right now, but you can find my information on there shortly. Thank you.
Yeah, perfect. Okay, so talk number 3 of this lightning session is going to be given by Fiona Victoria. She just started her PhD at the Oregon State University, but we've known Fiona for actually quite a long time. She sticks in my mind because she's the first person I'm aware of who was able to show a diffusion model being traded in a federated fashion. She showed it to the Flower community now maybe 16 months ago, And I think since then there's been some fantastic work in that direction, but in my mind, she was the first to do it. I'm really interested to see what her reflections are on that piece of work and what she might want to do next in her graduate career. But over to Fiona. I'm really delighted that you can join us today.
All right, thanks everyone, and I'm super excited to be here. I haven't actually met Nick and the rest of the Flower Labs team in person, so it was a very nice way to meet everyone in Florida yesterday as well. First of all, thanks to Nick and Flower Labs for letting me be here and present this incredible work that I've worked. It's been a while since I've followed up on this work, but it'll be nice to hear your thoughts on it and what are some interesting things you can see going about from here. So a little bit about my background. So I first entered into machine learning back in 2019, and then got a little bit into a small startup that works on building multimodal systems, specifically like audio, video, lip sync detection systems, and also quantization of neural networks in TensorFlow. And then I did my master's in CS, which is when I was first introduced to Flower because of my master's advisor, Dr. Afra, who's also very closely been collaborating with Flower Labs. And that's when I decided to do a thesis on federated learning for diffusion models. Since then, it's been a bit of a departure for me from FL, but I still try to stay connected with the rest of the team. And right now, my focus is mostly on AI for ecology and for species distribution models and for probabilistic graphical models. Or sometimes I do go back to industry and I do my research internships back in semiconductor manufacturing, which is a very different domain. But then I work on deep learning and Gen AI for the product yield optimization team. As you may know, these are some of the main architectures that might come into mind when I say a generative model architecture for any computer vision data that you may have. And the first is a variational autoencoder that you might all be familiar of, where you give it an image and it does its best to reconstruct it, but it also can give you very different variations, hence the name variational autoencoders, and that is due to the way it samples from the latent space. Then you're all familiar with the generative adversarial network, which is typically a two neural network model that kind of pit against each other, a generator model that tries to generate fake images, and a discriminator model that does its best to distinguish between the two of them. And by doing this over different iterations, it can finally create really good images of high quality. And third, you have diffusion models. It was kind of new back in its day in 2021, I guess. And what it does is effectively takes an image and it gradually starts destroying the image by adding in some noise to it. And over time, it actually ends up looking like a complete noisy image. And the great part about it is the actual reverse process where you use a neural network to slowly unlearn the noise that was added to it, and you can finally end up getting back the original image. Or you can also get tons of variations of the original image just because of all the data that it has learned during the denoising process. And there's, again, two ways to think about diffusion models. One is being unconditional and then being conditional. Unconditional is when you don't give any sort of prompts and it just starts creating images based on what it has learned from the training time. And conditional is what you are all used to doing today. You give it a prompt of give me an image of a panda sitting on a tree or something. You actually condition it to create what you wanted. So you kind of guide it in a way. So my work was mostly like a proof of concept. So I decided to go in an unconditional wherein I don't give a prompt, but then start seeing what are the newer areas of images it's able to create. Is it giving good mode coverage? So those are the questions that I was looking at. And these are three questions you usually run into, like how do you choose between a generative model? Like do you want a GAN or a VAE or diffusion? And the reason I went with the diffusion model is because it's the one thing that gives me high quality samples and a really good mode coverage. I do agree that diffusion models are a lot more heavier, so the sampling rate is a little slower, but at that time I think diffusion models was the one place that hadn't been tested in an FL space. And given that you know that a server can now start generating multiple variations of an image just based on what it was trained, it still doesn't focus on any sort of privacy or security that a FL system might. So a centralized AI/ML model is just not going to give you any privacy or guarantees at all. So that's when I decided to kind of move into a sort of a decentralized or a federated learning approach because of the simple question, do we really trust these centralized models with our own private data? So that became like a paradigm shift where you move in from a centralized ML of collecting all the data, keeping them on one global server, and then you train your algorithm on the server and then expose the API to the different clients. But then moving on from that is where you get into an FL space, where you actually choose the clients, which could be your mobile devices, any edge device, your laptops, a Tesla car, or any hospital organizations, and those would actually be your clients now. And you can actually broadcast your model, and the data never leaves those local devices. Only the model weights are those that are trained are updated back to the server. Some of the challenges of directly trying to integrate a diffusion model into an FL is that it first leads you to a problem of statistical heterogeneity or non-IID data. And this is something that can also compromise the model performance because different clients can have different variations of data. Next, you also have redundant clients. Not all the clients can always provide the good data needed to keep the updated model server really good. So there's usually redundant clients that you also need to take care of. And third, it's a little difficult to estimate the diversity of generated samples, especially in an unconditional diffusion model. So keeping those challenges in mind, we came up with a model called Phoenix, which was the world's first diffusion model trained in a federated learning setting that implements two strategies to overcome some of these challenges. The first are a data sharing strategy and a personalization and a thresholding filtering strategy. So why did I choose FLAR? So given that it was in 2022 or 2023, FLAR was kind of new at this time, but it was really cool to see how well their documentation was and how easy it was to get started in an FL. And that was something that I could not find in any other frameworks at that time. So first of all, FLAR provides data privacy and security with the way it has been created. It also allows you for really good collaboration. You can start spinning up any number of clients that you want, and you can also do a lot of simulations. You don't physically need to have that many number of clients. You could actually just have like 5 servers, but you could synthetically try to simulate what a FL might actually look like. And it also provides you ways to do personalization, like I think the previous presenter mentioned, personalization of these models in the local edge device is pretty important, and FLAR can also do that. Additionally, scalability. Like I mentioned, you could scale to simulate from 10, 100 to thousands of devices, and if you had the compute, you could actually scale them on your own physical devices. So the first strategy that I mentioned, which was data sharing strategy. So what happens in this method is that in the first pass, a small portion of the samples that you have are actually isolated and treated as global data. A single training is then would be done on this global data on the global server itself. And once one pass of this training is done, then all the global data with the updated weights are then shared to all the different 10 or 10 plus clients that you have. And then the actual FL training begins. So the reason for doing this first step of isolation and global training is to make sure there is enough representation of all the classes that might have been missed if you were to start training from just the clients alone. So for instance, client number 5 might have never seen an image of a cat, but those cat images might have been just in client 1 and 2. So the client 5 is never going to learn about it unless there's some way for it to have a little bit of an understanding of what a cat might look like. So that's why I do this initial pass of training it on the global server. The second approach is a little different, and this includes some personalization aspect of it to FL. So what happens is in first step, it's pretty much the same, the vanilla FL that anybody might do. You have a number of clients that are all being trained with your local data. Additionally, what happens is there's personalization layers. So if every client has a diffusion model, some of the last layers are actually adaptable to the data it offers. So you have some personalization layers per client. And then at some intervals, I start generating some samples in those local devices and monitor their performance. And this performance could be to see how high the fidelity or the diversity of these generated samples are. And by monitoring this performance, you have an approach to actually disconnect the clients that don't really contribute much to the global model. So if you see a fidelity or diversity of these generated samples being pretty low, you know none of these clients are actually giving valuable information. So I kind of monitor them for a couple of epochs, and if they don't really improve the performance, I end up disconnecting them so that they don't participate and end up ruining the rest of the global model. So Flower has some pretty cool ways, given that it's open source, that's the first big thing about it. You can actually go ahead and customize those functionalities that Flower provides. The first is you have metrics aggregated, which are the different metrics that you would like to monitor in your clients during the training time. So you could actually go ahead and add in your own markers that you want to track during the training. Additionally, you have ways to register and unregister clients that don't really give good performance. So that's also something that Flower provides. So kind of putting them all at once, I did like a comparison of a vanilla diffusion model on an FL and then the two new strategies that I just talked about. And then we could see that it outperformed by just sharing 4 to 5% of our total data. We do see a minimization of class imbalance because of the first training that we do in the global that I mentioned before. It is a stable training, and you can see a convergence, which is not something you can actually guarantee with a GAN or a VAE model. Also to keep in mind that this was 2 years ago, so that it was a pretty heavy computational model, and it took a lot of time to run, but I'm pretty sure diffusion models are now a lot lighter. There's a lot of quantization and pruning techniques being done in place to reduce the size of the model. So that's pretty much all I have. So this kind of just shows you how it's pretty easy to get started with any kind of generative model and kind of set them up into Flower, and Flower provides you enough and more capabilities to start playing and customizing them for your own use case. So thank you.
And by the way, all of the speakers here are in person, so after this session, feel free to have some real deep dive technical conversations about the work they're showing. But I'm happy to introduce our next speaker. His name is Matt Bauman. He's at the University. Oh, he was at the University of Chicago, but until recently. So when I first met him, he was at the University of Chicago, but I see now he's at Princeton University, and he presented some pretty fascinating work at one of our Flower monthly sessions, probably about 9 months ago, if I'm remembering correctly. What sticks in my mind was that it was a great investigation of both machine learning and the system requirements of building these federated systems. And so when I knew that we were going to come to the Bay Area and have some community events, I reached out to him to see if he would join us here. And he, I'm very happy to say he gladly flew in to join the community and give this talk. And I'm really fascinated to see his perspective, the work he's been doing, and how federated and these system kind of components really intersect. So over to Matt.
Awesome. Thank you, everyone, and thank you, Nick. It's really a pleasure to be here and get to have my first in-person Flower experience. As Nick mentioned, I'm now at Princeton University, but more specifically Princeton Plasma Physics Lab, which is a Department of Energy national laboratory focusing on the study of plasma physics for fusion energy, whenever that comes around. So with that mandatory disclosure that nothing I say is representative of the Department of Energy for many reasons. But yeah, as Nick also mentioned, I am a systems person by trade. I'm not an AI person, I just play one on TV. And so a lot of the investigation that I do is around how we can use FL in kind of a systems aware way. So I'll kind of be talking about this at varying levels of compute. First, we're going to start with the edge. We work with a precision agriculture group in New Zealand that focuses on bringing AI to the edge for rural communities and indigenous communities in New Zealand. And so we have these very cool robots that have a lot of compute capability and these hyperspectral cameras that basically just roam around in fields looking with these hyperspectral cameras at different crops, at the soil, and because you have this 148 channel image that goes all the way from far infrared to UV, you can have very good predictive models about soil quality, plant health, the minerals that are in the soil, the hydration of the plants in the soil. The problem is each of these images is 3 gigabytes, which is really a problem because even though these robots weigh a little over 100 pounds and have the equivalent of a couple GPUs of compute on board, they only have cellular connection. So when we are taking all of these images very, very rapidly, we can't send that because obviously 3 gigabytes per second is a lot less than the cellular capability of 150 megabits per second. And so this is one of the areas that we deploy federated learning because this allows us not only to make use of all these images that we're collecting, because obviously, like I said, we can't store them, we can't transfer them all, but it also then allows us to share this across different farming entities because New Zealand has very, very strong privacy laws, and that allows us to get a much more holistic and regional and locality-based view of these different qualities that different farmers are dealing with in terms of, like I said, soil quality, plant health, et cetera. Now, something that was said yesterday that I somewhat agree with, but also disagree with, is we have these big data centers of hundreds of thousands of GPUs, and we were kind of making the claim that we might not need those because we can have these disaggregated resources. However, why not both? So if we have multiple data centers that have tens of thousands or even hundreds of thousands of GPUs, we now have these massive AI workflows that can take advantage of these resources that are spanning hundreds of thousands of GPUs across the entire country and hopefully eventually across the entire world. There's this program called NSF Access where different institutions can basically contribute computing power, and then you, as a researcher or scientist, can apply for access credits and use these at all these different resources. What this then allows you to do is you can exchange these credits and get GPUs, CPUs, or whatever you want. So basically what we thought is, rather than just using one of these, if you have access to all these different resources, why not use them all at once? So we came up with a workflow management system because that's exactly what the world needs, is another workflow management system. But ours is best, of course. Jokes. So the idea here is that we take into account the relative buying power of these credits at these different computing facilities that allow us then to deploy tasks based on relative cost qualities, whether you care about getting really, really fast results, whether you care about really, really cheap results, different levels of quality, kind of a QoS-aware thing as well. We deploy this with a machine learning in the loop. So this is more of a disaggregated machine learning problem rather than a traditional FL problem, where basically we have these workflows running on each site simultaneously that are generating and evaluating molecules for battery design effectively. Can we find better catalysts? And so we deploy these kind of in a giant scatter-gather across all these different computing sites and then return all the results in kind of this very traditional FL/distributed ML pattern. We don't need to go in depth on the results, but the big takeaway is that results are coming faster, and we iteratively get these results back faster because each round is shorter and shorter, because with each execution, we learn more and more about the resources that we're deploying to. And so we're almost kind of we kind of call this tongue-in-cheek FL for FL, because we're using this distributed knowledge collection about the resources to then feed back into the system itself. So next, scaling this up even bigger from NSF to now DOE. Very, very recently, within the last month, the Department of Energy has announced this idea of the American Science Cloud. The idea being we have all of these amazing user facilities that are physical science facilities and also compute facilities at the different Department of Energy national laboratories. And rather than folks at Princeton Plasma Physics Lab only being able to use PPPL resources and people at Argonne only being able to use Argonne's resources, the DOE is a single department, and so we should be able to use all of the resources across all of the different laboratories. And so we have, somebody mentioned this yesterday, I was kind of shocked, this infrastructure called the Energy Sciences Network, ESNet, that connects all of the Department of Energy sites with extraordinarily high bandwidth networks. I think our highest bandwidth now for a single link is something like 2.4 terabits, which is pretty solid and allows us to do really, really cool things. But the way that we see this is a what we call a continuum of science facilities. So we have these different exascale systems. There are 3 to 4 of them now, depending how you count it, across the country at these different DOE facilities, as well as these different science user facilities. So I just put on here, there are synchrotron light sources in Brookhaven and here in Berkeley. And then we have our spherical tokamak at PPPL. So what we really hope to do is being able to leverage both the compute resources and this high bandwidth network to pair those with the different science user facilities that might not be right next to each other, physically speaking. And so we think FL and this disaggregated machine learning is the perfect way to do this. Building off of this, we have the idea, this other initiative that was announced alongside the American Science Cloud, which is called ModCon, the Department of Energy Transformational AI Models Consortium. Really great naming scheme. Which is, the idea here is to then leverage these resources. Once we have this kind of pool of compute, this computing continuum, we can use the local data from all of these different science facilities to create science-specific foundation models and leverage those compute resources to do this using this disaggregated data collected by these 14 different national laboratories. So what comes next? A couple of areas that we're really interested in. Maybe these will be, I won't go so far as to say inspiration for what you guys are working on today, but just cool questions to think about. Topology-aware federated learning. Traditionally, federated learning is very flat. But when we start thinking about these big graphs of compute resources and data resources, we can think of these different fabrics, whether it's data, compute, or tasks, as topologies and doing interesting things with topologies. Following from that, we have this idea of hierarchical FL and personalized FL, where perhaps different organizations, different groups within the Department of Energy, different labs might have specific requirements of, maybe we're willing to send our data to one other lab, but not the third lab because we don't like them or whatever. And then building this, once we have these different resources, these foundation models for science, actually deploying these as federated AI agents. So this goes a lot to this distributed inference infrastructure that was talked about a lot yesterday, and being able to agentify a bunch of workflows. This is actually, this diagram here is the agentification of that catalyst design experiment that we talked about earlier. And finally, too, breaking from the pattern of traditional FL, one of the applications we are super interested in is taking this compute resource map that we have, this energy sciences network, and not just figuring out how to best map tasks to where the data is located, but also saying if we are able to move the data, how do we kind of have this optimal mapping of moving data and compute simultaneously to map onto the resources that we have available at any given time. So with that, I'll say thank you for listening. I'm happy to take questions or chat later. Yeah, thank you very much.
We have Cody Kendall. Cody Kendall is working on a coding agent called Leonardo. I'm super excited to see and hear all about Leonardo. And thank you, Cody, for joining us today. Over to you.
So my name's Cody. I'm the founder of Llama Press. And today I'm going to talk to you about our latest agent, Leonardo. So Leonardo is a coding agent that builds full stack web applications directly in the browser. Let's do a quick demo. Let's start with something simple. Let's just say, what are your capabilities? And what Leonardo is going to tell you is that he's a coding agent, that he builds Ruby on Rails full stack applications. He uses Tailwind, he uses Postgres, and that he runs on a framework called LangGraph. Have any of you heard of LangGraph? A couple? Have you heard of LangChain? So LangGraph is an agent orchestration framework that's put out by LangChain, the company. All right, let's try it out then. Let's say, great. Say, please take this info and embed it on this page we're looking at. And so Leonardo can see what you see here on the right-hand side. You have this iframe that's kind of displaying the application. Say save it on the home page. Then you have this chat agent that's on the left-hand side that you can talk to. Leonardo has a handful of tools, such as being able to write to-dos, which this is a common feature of many agents now, as they are able to plan and create tasks for themselves. Leonardo is also able to search through the file system. It's able to read any files that are in the file system, and is able to actually write code as well to files in the file system. So here you can see that he identified where the home page was saved at by searching around the file directory. He also has access to Git, so it can save code, commit, push, pull, etc. And here you can see it's actually now editing the home page. So let's go ahead and go back. Let's see if it did it correctly. Let's refresh this page. And here it is. So why build this thing, right? Well, for me personally, I just love to build software. And this is something that makes it easier to build more personalized software. Here's a quick question. How many of you are using ChatGPT at least a couple times a week, right? I think everyone should probably raise their hand, hopefully. How many of you have tried like Claude? You've tried Claude? How many are using Claude just as frequently? Okay, quite a few, that's pretty good. How many of you have memory mode turned on in ChatGPT? Okay, a little bit less, but what's interesting with memory mode is ChatGPT will remember very specific details about your life, about what you're doing. But if you've ever tried to switch over to Claude or to Gemini or these other providers, one of the drawbacks is that you don't get to bring all of that with you, right? So you have this, personalized experience with ChatGPT that you don't get to benefit if you switch to something like Claude or Gemini. And I actually think that's a little bit of their business model that they're banking on, is they're hoping that the more that they can kind of know about you, it's going to be harder to switch to other providers. But what if we wanted to be able to switch out providers? What if we didn't want all of our personal life and context locked into a single company? And that's where if you have an open kind of system where you can have it save information about you, and you can easily swap out to other large language providers, and you can maybe run this software on your own computer, or you can run it on your own server, then it really frees you up. And it means that you can swap out providers, be completely independent of them. The other thing too, though, is that we all love talking to a chat interface, right? That's how we all use software, right? Is that the future? Is the future just all chat? I personally don't think so. I think the future is actually a mix, right? And Andres Kaparthi had a really interesting talk at Y Combinator where he talked about the future of software being, you have this kind of chat interface on the left-hand side, and then you have a more traditional user interface on the right-hand side. So that's another reason why I wanted to have kind of an open alternative to something like ChatGPT. Let me show you this specific application, and maybe this will, make it a little bit easier to conceptualize where I'm going with this. But I'm going to go ahead and sign in here. And this is actually my personal journal, right? So I've had it scaffold up a database that has journal entries. I have it remember my goals. I have it remember my tasks. And by just talking to Leonardo, I can have it create any database that I want. I can have it model out my world, how I view it, how I see it. Another company I've been working with, actually a couple of friends of mine, is we're building a personal finance agent that you can talk to and essentially get help with your personal finances. Let me just log into my account here really quick. And so this is actually hooked up to my bank account. How many of you want ChatGPT to have unfettered access to all of your bank transactions? A couple. Okay, you're brave. You're very brave. But what if you wanted Claude to, maybe switch to Claude eventually, right? Right now, ChatGPT, they wouldn't let you do that very easily, right? Claude wouldn't either. But in this case, it's kind of cool because you can create these very, like I said, kind of a personalized software experience. And you can also embed LangGraph directly into the application as well and make it end user facing. So this is kind of like an admin view on the left-hand side, this chat interface. I wouldn't want to give this to anybody who uses this application because they could drop the database or they could read everyone else's bank information. But you do want to expose kind of an end user facing large language model agent as well. So in this case, we have this agent in here, and we can say, what is my progress toward my goals? And then it can search through, check for the financial goals. It sees I have 2 goals in here. And then you can even create like interactive charts and different things that's very specific to your domain. In this database, we're saving things like goals, like budgets, like account information, etc. And then you kind of have this personalized experience where it can remember your goals, remember all of that. So all of this is completely open source. In fact, I'll show you the source code right here. Couple quick points. Leonardo is a type of a deep agent. This is a concept that was recently popularized by Harrison Chase at LangChain. And a deep agent just essentially has a couple of capabilities. It can do long-term planning. It can have access to the file system. Usually they have very long and detailed system prompts, and it can also spin out sub-agents to keep its context window nice and clean. So this is the same architecture that tools like Claude Code uses or Cursor Agent Mode. But really it's just the same kind of architecture where you have a React tool calling loop, where you have a reasoning step, then you have a tool calling step, and it just runs in a loop. The code is actually surprisingly simple. It's here in roughly 30 lines of code, at least the interesting parts. Like I said, this is also open source, so there's a QR code. You can go and look at the actual implementation. And yeah, that's Leonardo. Any questions or thoughts from anyone?